All right, welcome back to lab, part two of this RL series circuit. Now let's talk a little bit about voltage, okay, in a series RL circuit. So voltage across the components in an RL circuit must add up geometrically due to the phase difference between VL and VR. And let's talk about what this picture here means. So here's your current coming in. Here's your current total. And you'll notice that across the resistor, your current and your voltage are perfectly in phase because it's a resistive component. It's passive by nature, where the voltage across your inductor is going to be 90 degrees out of phase, okay? And because of Eli the Iceman, voltage will lead the current, and you can see that. So right here, your current, okay, is at 0, and the voltage for your inductor is at 90 degrees already. So what that means is as we've talked about, your current will be somewhere in between that. Your current total and your voltage total will be somewhere that will be somewhere between 0 and 90 degrees. If it's 90 degrees, it's a purely inductive circuit. If it is 0 degrees, it is a purely resistive circuit. So if you have a resistor and you have an inductor in a series circuit, it will be somewhere between 0 and a positive 90 degrees. Okay, so since VL leads VR by 90 degrees, they can be graphed like this. Okay, and you guys know that I'm a big fan of these 90-degree angles, and we'll be talking about this a little bit later. We can graph our X of L and our R the exact same way. Okay, so here's my VR, here is my VL. Okay, the magnitude of E is the geometric sum of VL and VR. So when you would use the calculation that's about to come up is if you didn't know what your voltage total was, or if you wanted to verify your measurements or your calculations. Okay, so here is the formula right here. So the voltage total, as they have identified as E, okay, which is totally fine. I may have identified as VT. Is the square root of the voltage across the inductor here and squared plus the voltage across the resistor. Okay, and this will give you your voltage total here if for some reason it's not given. So you guessed it, we now need to bring up our iPad, and so we can continue to with our formulas. Okay, so our next formula that we need to write down is, and I'll use voltage total here. All right, voltage total equals the square root of the voltage across the inductor squared plus the voltage across the resistor squared. Okay, oops, let me get that out of the way so you can see it. Sorry about that. Okay, and we'll go ahead and do the phase angle as well, your other formula for your phase angle. And again, in lab, we will verify this. We will verify that they are the same. If you figure out your phase angle via inductive reactance and resistance, or the voltage drops across your components, your phase angle should be within 1 to 2 degrees, okay, depending on how you round, all right, or the accuracy of your measurements, okay? So we'll go ahead and add that here. Phase angle equals the inverse tangent over the voltage across L over the voltage across your resistor. And this formula right here is going to be pretty important when we're doing our labs, because remember that voltage measurements are the only measurements that we're going to be able to get. Okay, so this will be very, very important. All right, so let's go ahead and continue on. All right, so For the circuit shown, the magnitude of the source voltage is found as, all right, so I think the answer might be up here. Let's see. Oh, no, it is, but let's run through it anyway, okay? Sorry about that, guys. I thought I blocked it off. So let's go ahead and pull up the calculator here, and we'll run through this. So if I want to know what the voltage drop is, I'm going to take 3 squared plus 4 squared equals 25. And then I'm going to take the square root of that, and I get 5 volts. Okay, and that would tell me what my voltage total was. So if you were only given voltage drops, or you'd already calculated out your voltage drops because your current was available, this is how you could figure out your voltage total. Or you could figure out what your needed voltage total should be. So if you know you need a specific voltage dropped across something, this is the way you could reverse engineer that. All right, so now let's go ahead and figure out our phase angle here. All right, and I hope you can't see it on the other side there. All right, so we knocked that out of the park. All right, so for this circuit, let's go ahead and figure out what our voltage, what our phase angle is going to be. So to do this, I will just go ahead and steal this little sign here. Oops. Oh, well, you know, we'll just walk through it anyway. We've done this formula a couple times now. So we take the inverse tangent of 3, which is your voltage drop across your inductor, and divide it by 4. Okay, and this is going to give you 36. Now, I do want to show you a couple of things here about this, and just some patterns that are really important to pick up on. You can tell here that this circuit is more resistive than inductive for a couple of reasons. And there's a couple of reasons and ways you can see that. The first, you're getting more voltage drop across your resistor than you are your inductor. What that means is your phase angle is, first of all, it's more resistive, so your phase angle is going to be less than your less than 45 degrees. And let me show you this here, because this is really, really important, okay? So let's say, so if I were to draw up a 90 degrees here and make this 45 degrees, this is VR or just R, okay? And if this is VL or X of L, all right, if my resistor is larger than my X of L value, okay, I will be less than 45 degrees, okay, all right. If my X of L is larger than my R, I will be greater than 45 degrees. Okay, remember the alligator eats the bigger number. Okay, that is the same with your voltage drops. Okay, remember your voltage drops are a reaction to your X of L and your R. Okay, and as your frequency changes and your X of L changes and gets higher, your voltage drops will change. Okay, it will go from being more resistive to more inductive as your frequency goes up. Okay, what do I mean by that? Well, let's say I'm at 100 hertz, okay, and here is my phase angle. Well, as my frequency goes up, my phase angle will rotate as well. And I talk about this in the lab quite a lot. And this is the point of the lab. The point of the lab is to see how frequency affects this. And you will see that as my voltage drop goes more across your VL, because your X of L gets larger as your frequency gets larger, your phase angle grows. Okay, this is a really important feature of an RL series circuit, and let's prove that right now. Okay, let's go ahead and prove that. So let me scoot this out of the way so you guys can't see it. let me go ahead and show you this. So let's just say we were getting a, well, let's just reverse it. Let's say we had 4 volts dropped across our inductor. We divide that by the 3 volts dropped across our resistor. We do our inverse tangent, and now we're at 53, which is greater than 45, obviously. Sorry for stating the absolute most basic thing, okay? So, okay, so let's go ahead now and do a quick review of inductive power. Now, we talked a little bit about this last week, and so we'll just continue on with that lecture here, okay? So there are 3 power values associated with an inductor, okay? We have the resistive power. Now, the resistive power, okay, sometimes PR, sometimes referred to as PT, which is confusing because then people think it's power total, but it's actually not. The power PR in this PowerPoint is what they're using. In this case, it can be the winding resistance that is measured in watts, but really now it's going to be the power across the resistor, okay, in these circuits. Then we have reactive power, okay, which is stored in the magnetic field of the inductor, okay, this is the wasted stuff, all right. And then we have the apparent power. This is a combination. In some ways, we could identify this as our power total. They identify it as VA, and VA is used to rate the power on all most inductive things. There are some other ways to do it, but if you look at a transformer, always rated in VA. When you're sizing out a house, it's rated in VA, volt amps, not wattage, things like that. And we talked about that in the last slide, the last week as well. Okay, and here's everybody's favorite picture, right? Okay, here's your total power. Here's your wasted electricity, and I want to emphasize that it's wasted, okay? It's just gone, all right? And it gets burnt out, and this is the effect of having the voltage and the current out of phase with each other. And then here's our real power, whatever we're actually getting across our load, okay? So if you look at like a factory or something, this would be the factory, this would be the wasted energy, and this kVA is what they're going to be paying for. Okay, so let's go ahead now and solve for PX and PR. All right, now I don't love the way they do it. I'm going to show you how they do it here, and then when we go into our labs, I will show you the way that I like to do them. Okay, this is a very clean-cut way they do it, so you know, I'm not hating on it by any means. All right, so first, what they do here is they are assuming that you know the current. Okay, and so if you know the current and you know the inductive reactance, this is a great way to do it. You would just go ahead. Here's your voltage total. They're indicating this as 15 milliamps. So you would take 15 milliamps, 0.015 squared, multiplied by 30. Okay, let's go ahead and take a look at what value that actually comes out to be. Move this out of the way. Bring up the old calculator. Bring this up. So clear this out. We're going to do 0.015 because it's in milliamps. We want to convert it to amps. Square it times 330. All right. Hit equals. And here we're saying that we're getting about 74 VARs, milliVARs. Okay, let's see how that comes out to be. Hey, look at that. Nailed it, knocked it out of the park as expected. So now let's go ahead and do that again. This time we're going to use the resistor value of 0.015 times 220. Oops, forgot to square that, common mistake. Squared times, all right, one more time. It's just like being in class when I'm making mistakes. All right, times 220. and they're saying that we're getting about 50 milliamps or 50 milliwatts because this is across the resistor. Let's check that out. They had 49.5, and that's where they rounded to. 49.5. All right, very cool. Very cool. Now, those are some of the ways to do that, okay? I am going to give you a formula right now that I feel like is a little bit clearer and a little more straightforward. You can write those down if you want. It's not what I'm going to do, but if you want to, you of course can. So, a way to get your power across your resistor is you take the voltage across your resistor times IT. Okay, I think that is the most clear-cut way to do this. All right, then we'll scoot over here. The voltage across your reactive component is your voltage across, in this case, X of L, or just L. All right, voltage across your inductor times IT will give you that. Okay? All right. Now for the next slide, how do we figure out our apparent power, our VA, all right? The total power, what are we going to be charged off of? And, okay, this is really, really important to be able to do, and it will help to factor in our phase angle and our power factor as well. So in this case, what we want to do, we have kept our values right here, all right? And so again, just like our impedance, our voltage total, our power total is calculated using Pythagorean's theorem. Now, you can convert this if you want to watts or VAR out of milli. But since they're both in milli, it is a little bit easier just to keep them in that form, okay? And that's what I'm going to do here. So I'm going to take 74.3 squared plus 49.5 squared. I'm going to equal that out. Then I'm going to take the square root of that value, and I'm getting 89.3. All right? They're saying 89.3 here. Let's take a look. Nailed it. Look at that. Perfect. That's great. So let's go ahead, and what we want to do now is go ahead and write that formula down here, okay? That PX formula. So I'm going to come here, go back. Oops. All right. So let me bring this back up again. Sorry for the confusion. Here we go. So PAPP equals the square root of PX squared plus PR squared. Okay? All right? And so this is how you calculate that out. This is one of the ways you can calculate it out. There's actually another way to calculate it out as well, which is a little bit easier. And the other way you can calculate out the apparent power, well, there's actually a lot of ways to do it, but you can also take the voltage total divided by the current total. All right, these are all legitimate ways. It's all about what you know. Okay, it's all about what you know. And we'll use some of these formulas, and I'm going to show you a really cool trick here in a little bit to overcome that. All right, so we'll move on back to here. Now for the power factor. All right, and so the power factor for this is the ratio of the resistive power to the apparent power. Okay, and the closer you are to 1, the more resistive the circuit is, and the more actual power you will be drawing, the less foam you'll have at the top of that beer. Okay, so let's go ahead and first of all, we want to write this power factor formula down. Okay, All right, it doesn't change that much from the other one that we talked about last week. So it's just the main difference between these is that now we have a resistor. We're not just using the resistor of the windings on the inductor. All right, so power factor equals PR divided by, hopefully I can get this in there, A P P. All right, oops. Let me scoot this over so you can see it. Sorry about that. There we go. Hey, that's not too bad. The power factor equals PR over APP. Okay, and so when you do that, and this is the formula for calculating out your power factor. Okay, so let's go ahead and look at this. Oh, and I skipped something. I apologize. All right, sorry about that. Now, the other way we can calculate out our phase angle is to use our power formulas. Now, our powers will be the same as your phase angle will be the same as your power. Okay, or the phase angle will be the same throughout the circuit. And so in this case, they have some values here. We can go ahead and run this through the calculator to calculate out our phase angle. I apologize for skipping this part. So again, this is another formula that you're going to want to write down on your board, on your sheet of paper. I'll just write it over here so I have a little bit more room. The inverse tangent of the power, the power across your reactive component, in this case Px, over PR, closed parentheses. Okay, and you can see that formula right here, but I wanted to show you writing all these formulas down. Okay, now now in lab at least, it's going to be about knowing which formula we actually should be using. Okay, so let's go ahead and perform this calculation here and see how we come up. What do we come up with? So now the question here, let me ask you this question. Is this going to be more inductive or more resistive? Meaning, if it's more resistive, it's below 45 degrees. If it's more inductive, it will be higher than 45 degrees. Okay? Scream the answer out loud. I can't hear it. Okay? So let's go ahead and find out. 74.3 divided by 49.5 equals, I'm going to bring the inverse tangent up, 56. Okay, that means our phase angle here is 56.3. Okay, and that means that it is more inductive. Okay, with the frequency and the inductor size and the resistor that's in there, we would have a phase angle of 56.3. Okay, all right. So I'm going to go ahead and wrap this portion of the lecture off. This portion. Okay. In the next portion, we are going to run through a couple circuits, and I'm going to show you the hints and tricks on how to make this math easy when you are doing it on paper. Okay. All right. Thanks for watching. We'll be back here in go ahead and click on to the next video.